Hi everyone! In this video, you will learn about collisions and the conservation of momentum. If you are new to this channel, please do not forget to subscribe, hit the bell, and do some comments. I post the channel videos at least twice a week, every Tuesday and Thursday. So let's get started! Our lesson for today is about collisions and the conservation of momentum with the following goals. Number 1, to define collisions and identify different types of collisions. And number 2, to state the law of conservation of momentum and solve problems involving conservation of momentum in collision. What are collisions? In general, collision is an interaction in which two objects strike one another and the net external impulse is zero or negligibly small. Momentum is conserved. Collisions can involve two or more objects. Some examples of collision. There are two types of collisions. The first type is called elastic collision. It is a type of collision between two objects in which the total kinetic energy as well as total momentum of the system is the same before and after collision. Recall that the kinetic energy K equals 1/2 mv squared and momentum P equals m times v. Example of elastic collision. In this collision, there is a momentum transfer from one object to another. The total kinetic energy as well as the total momentum of the system is the same before and after the collision. The second type of collision is called inelastic collision. It is a type of collision in which the total kinetic energy of the system is not the same before and after the collision, even though the momentum of the system remains constant. Inelastic collisions are of two types. The first type is perfectly inelastic. This occurs when the colliding objects stick together after the collision. The second type is inelastic, when the colliding objects do not stick together but some kinetic energy is lost, as in the case of a rubber ball colliding with a hard surface where the ball is deformed. Some examples of inelastic collision. In this collision, the balls do not bounce, they stick together. Other examples of inelastic collisions, here the objects stick together after the collision. The law of conservation of momentum. One of the most powerful laws in physics is the law of conservation of momentum. It can be stated as follows. In the absence of an external force, gravity or friction, the total momentum before the collision is equal to the total momentum after the collision. So P total before equals P total after, or P total initial equals P total. The total momentum of all objects interacting with one another remains constant regardless of the nature of the forces between the objects. Initial momentum equals final momentum. For two objects colliding, the conservation of momentum can be written as m sub 1 times b sub 1i plus m sub 2 times b sub 2i equals m sub 1 times b1f plus m sub 2 times b sub 2f. It applies to any interaction between objects and says the momentum of all the objects prior to an interaction must equal the momentum of all the objects after an interaction. In other words, the total momentum never changes. This doesn't mean that the individual momentum of an object never changes. Obviously, it does. In solving problems involving momentum and collisions, the following equations are helpful. 1. Momentum P equals the product of mass and velocity. Number 2. Conservation momentum says P before equals P after. Third, conservation of kinetic energy. The kinetic energy before equals kinetic energy after. For problems involving elastic collisions, there are two useful formulas. Letter A, m sub 1 b sub 1i plus m sub 2 b sub 2i equals m1 times b sub 1f plus m2 times b sub 2f. The second equation is taken from the conservation of kinetic energy. B sub 1i plus B sub 1f equals B sub 2i plus B sub 2f. Number 5, for inelastic collision, we assume perfectly inelastic collision. M sub 1 times B sub 1i plus M sub 2 times B sub 2i equals M sub 1 plus M sub 2 times B sub f. Let us do some examples. Number 1, what is the velocity of the eighth ball after the elastic collision below? In the figure, before the collision, the velocity of the white ball is 2 meters per second. Its mass is 0.25 kilogram. The velocity of the eighth ball or the black ball is 0. Its mass is 0.25 kilogram. After the collision, the white ball stops and we are looking for the final velocity of the black ball or the eighth ball. Solution. Since the collision is elastic, then momentum is conserved. We let small m sub w equals mass of the white ball, which is given to be 0.25 kilogram. B sub wi is the initial velocity of the white ball, which is also given to be 2.0 meters per second. B sub wf is the final velocity of the white ball, which is 0. M sub b is the mass of the black ball or the eighth ball, which is 0.25 kilogram. B sub vi is the initial velocity of the black ball, which is 0 meter per second. And B sub bf equals the final velocity of the black ball, which is to be found. Then using the law of conservation of momentum, the total momentum before the collision equals the total momentum after the collision. Or in equation form, m sub w times b sub wi plus m sub b plus times b sub bi equals m sub w times b sub wf plus m sub b times b sub bf. Substituting the values, 0.25 times 2 plus 0.25 times 0 equals 0.25 times 0 plus 0.25 times BBF. Solving for BBF, it is equal to 2.0 meters per second to the right. Example number 2. A 0.05 kilogram marble moving to the right at 2 meters per second strikes head-on a 0.02 kilogram marble moving to the left at 3 meters per second. What is the speed of its marble immediately after the collision? Assume the collision is perfectly elastic. Since there are two directions of motion here, we assign positive value to the velocity moving to the right and negative value to the velocity moving to the left. Solution. Since the collision is perfectly elastic, we apply both the conservation of momentum and the conservation of kinetic energy. By conservation of momentum, m sub 1 times b sub 1i plus m sub 2 times b sub 2i equals m sub 1 times b1f plus m sub 2 times b sub 2f. Substituting the values 0.05 times 2 plus 0.02 times negative 3 equals 0.05 times b1f plus 0.02 times b2f. Simplifying, we have 0.05 b1f plus 0.02 b2f equals 0.04. We call this equation 1. We need another equation because there are two unknowns here, b1f and b2f. The second equation can be obtained by using the conservation of energy. b1i plus b1f equals b2i plus b2f. Substituting the values and simplifying, we get b1f minus b2f equals negative 5. And this is our equation number 2. So, solving the two equations simultaneously, we get b1f equals negative 6 over 7 meter per second, which is moving leftward, and b2f equals 29 over 7 meter per second, moving rightward. Example number 3. Sarah and Mara are initially at rest. Sarah has a mass of 45 kilograms and Mara 30 kilograms. After the push-off, Sarah is traveling at 4 meters per second to the left. What is Mara's velocity after the push-off? Since the collision is elastic, then momentum is conserved. We have ms b sub si plus m sub capital M times b sub capital Mi equals m sub s times b sub sf plus m sub capital M times b sub capital M f. S stands for Sarah and capital M stands for Mara. Substituting the values and then simplifying, we get b sub mf equals 6 meters per second to the right. Example number 4. During a goal line stand, a 75 kilogram fullback moving eastward with a speed of 10 meters per second collides head-on with a 100 kilogram lineman moving westward with a speed of 4 meters per second. The two players collide and stick together, moving at the same velocity after the collision. Determine the post-collision velocity of the two players. This is an example of a perfectly inelastic collision since the two players stick together after the collision and they move as one. So, for perfectly inelastic collision, we use the formula m1 times b1i plus m2 times b2i equals m1 plus m2 times bf, where bf is their common velocity. Substituting the values and simplifying, we have bf equals 2 meters per second moving westward. Example number 5. A 6 kilogram fish swimming at 1 meter per second swallows a 2 kilogram fish that is at rest. Find the velocity of the fish immediately after lunch. Solution. This is an example of a perfectly inelastic collision, since the two fish stick together after the collision and they move as one. So, for perfectly inelastic collision, we use the formula m1 times b sub 1i plus m2 times b sub 2i equals m1 plus m2 times bf, where bf is the common velocity. Substituting the values and simplifying, we get BF equals 6 over 8 meter per second or 0.75 meter per second. Example number 6. Now the 6 kilogram fish swimming at 1 meter per second swallows a 2 kilogram fish that is swimming towards it at 2 meters per second. Find the velocity of the fish immediately after lunge. In the figure, before the collision, the 6 kilogram fish is swimming to the left at 1 meter per second, while the 2 kilogram fish is swimming to the right at 2 meters per second. This is still an example of a perfectly inelastic collision since the two fish stick together after the collision and they move as one. So for perfectly inelastic collision, we use the formula m1 b sub 1i plus m sub 2 times b sub 2i equals m1 plus m2 times bf. Substituting the values, simplifying, we get b sub f equals minus 0.25 meter per second. The minus sign indicates that both are moving to the left after the collision.